Hello YouTube. Today we are going to talk about how to build an actual laser from complete scratch. If you want to tune in for this video, you can find out how to build a laser from some of the most basic imaginable things you've ever dreamed possible, and at the same time have a lot of fun doing it and learn something along the way. You'll be making this laser from basic supplies such as fluorescent markers and small metal parts you can get from a local home improvement store. This is as simple and rough and down to scratch as you can get when it comes to building a real working laser. And lasers are still considered part of the high-tech world, yet this is a laser that you can build on a very basic level at home using almost supplies that you could find around your home, scrap, with maybe a couple of trips to your local home improvement store or Walmart, and maybe a simple power supply you could purchase off of eBay for only $3. If all you want is a laser, you can easily buy one. Just keep in mind that this is a proof of principle approach to doing this. This is not the kind of laser you build that is going to draw a crowd or that you're going to be able to do a laser light show with. This is about what you can do, not what you can buy. This is like a blank canvas, and you're painting something from scratch. And you're doing it for the pleasure you get out of doing it. If you want something that's a good picture, you can go buy a camera or go buy something somebody else painted. So just keep in mind the purpose of this is to learn from doing it and to enjoy doing it. It's not to get a laser that you're going to be able to use for anything or that's going to compare in any way to the kind of laser you can buy. Okay, I'm going to show how easy this laser is to construct. Now, this is the saddle threshold that you're going to use for the laser electrodes and for the actual capacitor. See, the width of these and the length of them defines the area, which then in turn defines the actual capacitance based upon the physical area of the plates, the thickness of the dielectric, and the dielectric constant. I think I measured these at like 4.2 nanofarads. If my memory's correct. But if you look at this, there's the one detail you want to pay attention to. The size that you're going to face towards each other and make electrodes out of, you want to file a curve at those ends right there, and then you can touch it up with some fine sandpaper. But the point is, you want it to curve away from the discharge, because if it doesn't, you're going to encourage sparks to take place at the ends. If these sharp ends here were used for the laser electrodes, sparks would tend to occur right there at the ends where those sharp edges are at. So this is very important. You want to just get a smooth taper. It doesn't have to be any special angle or anything, but just a smooth taper away from that area where that discharge takes place. This was used for a smaller laser. That's why I'm using it as an example. The actual electrodes I'm using for this laser are like a yard long. Well, actually, they're 35 inches and 7/8, I believe is what they are when I measured them. These are going to be the electrodes, and they're saddle thresholds that you can get out of a hardware store. And the reason you're using this, again, I'll use this for an example, is because the edges of these are raised. You get your laser discharge to occur above the surface of the dielectric. At least that way, there's a little clearance there. I think it also makes the discharge probably better because it will tend to be less likely to track along the edge or the surface of the dielectric, which is not what you want. These are transparency films for use in copiers. This is one of the most important parts of the project. Sometimes they're sold as overhead projector transparencies, right-on overhead projector transparencies, but they're all the same thing. They're just kind of razor thin pieces of plastic, and it's a rigid piece of plastic. It's not like a garbage bag where it's all crinkly. It's a nice straight rigid piece of plastic that is paper thin, like 5/1000th of an inch thick. And for these electrodes, these plastics here are like 8 by 11. They're actually smaller than that. So they're not going to be big enough to cover the entire length of these electrodes. But that's not a problem. What you're going to do is you're going to take them and lay them down like this. And I'm going to move these out right here a minute. You're going to take them and lay them down. And then you're going to just slightly overlap them like this. Because they're so thin and the electrostatic charge creates a great enough force to where it pulls them together and you're not going to have any electric sparks jumping between the gaps there. So that's the way you're going to do it, and I wanted to show you that because once I put the aluminum foil down, it's actually going to be harder to see these. But you're going to put them like this, along the length right here. These are going to be your dielectric. You're just going to have metal on both sides of them, and that's what you're doing to form a capacitor. So you're going to take some ordinary kitchen aluminum foil and you're going to lay this aluminum foil down like this. And then you just want to smooth that out like that. Make sure it's nice and smooth. That's one of the beauties of these things is you can actually use aluminum foil. If I wanted to increase the capacitance, I could also make the top plates bigger by adding aluminum foil in addition to the actual saddle thresholds that are used for electrodes. And I could increase the area that way. It's not necessary for this, at least for this demonstration. If you get the capacitance too high beyond a certain point, it probably won't work as well because your discharge becomes too slow. You have to have an extremely fast electrical discharge or it doesn't work. Now we're going to lay our sheets down here like this. I'm overlapping each transparency just a little bit, maybe about an inch or so. It's no exact number or anything, but you just want to overlap it a little bit. This is easier done on a flat surface like glass, but I did it on this really good quality piece of wood here because I wanted to get it up high enough to where it wasn't so hard to get the laser up where it could pump the dye. So now we've got our transparencies on there, and it really is hard to see these things against this aluminum foil. Then you're going to take the electrodes right here, and we're going to put them right there like that. Okay, and we're going to take that and put this one right here. Now, here's the secret to making a laser like this one. The real trick here is to get everything right as far as the spacing. Theoretically, a laser like this shouldn't work. It's too long. For an optimal design, 9.5 inches would be, I think, ideal. The reason why is because the pulse is about 800 picoseconds long. And in that length of time, light only travels 9.5 inches. This right here, I think at the expense of efficiency, you're able to get a dirty design that you get more power out of. And you're able to do that because you're going to slightly make one end narrower than the other. And what that causes to happen is most of the laser light comes out the wider end instead of the narrower end. In fact, you get almost no output from the narrower end. And it takes a little playing around and adjusting to get it like you need it to get the best output. But that's what you're going to do. Now, there's some theories as to why that happens. One of the theories is that when it discharges, the electrical discharge starts down here first and then moves up here. And it's essentially moving at the speed of light. At the same time, the light is being amplified, the photons that are traveling that way, and they're being amplified through stimulated emission. So you, in effect, cheat the length limit on this thing to where the light can continue to be amplified as it moves with the electrical wave. Therefore, you're not limited in the length that you can make it as you would be if the discharge was taking place uniformly across one side to the other. My theory is you're probably sacrificing some efficiency, but for the purposes here, we're trying to get a laser that is very simple but will pump a homemade dye without nitrogen. So the next step is we're going to take our aluminum foil and we're going to fold it up here like this. One of the pitfalls of having the thing on a piece of wood is that I've got to curl some of the aluminum up, and that may cost me something in inductance, but I think we're fine for the most part. Also, sparks will very much be encouraged to track along the surface, which is one of the worst problems with this type of laser. So I think we're going to move electrodes a little closer over this direction, get them a little further from where I intend the spark gap to be, so that sparks will have further to travel across that dielectric surface. Take a bolt with acorn nuts. This is another very important thing right here. You want to get acorn nuts because you want the spark gap to be basically an electrical breakdown between two balls of metal. You want acorn nuts because that's a convenient way to get metal balls for these sparks to jump between. The charge builds up, and when the potential is high enough, you have sparks that jump between these two balls and it discharges the capacitor. So we're going to put this right here like this. Put the other one right here like that. We want the distance across this dielectric to be great enough to where sparks are not just going to track along the surface, because a spark will travel much further across the surface of an insulator than it will through the air. So let's see, I'm going to narrow this in a little bit and make it, and this is a little wider down here. That looks like it may be a little over a millimeter, and this over here looks like it may be closer to 2 or 3 millimeters. Now we're going to put an inductor right here, and the reason for the inductor is to allow both sides to charge up. But then when the discharge takes place between the electrodes, it's too fast to go through the inductor. That inductance, though, it's just an arbitrary number of turns, and it's a piece of wire I grabbed and twisted up like that. Any amount of turns at all, the inductance is going to be far too high, and it's going to go across the channel rather than going through there. The worst thing about these is these spark gaps. They're very loud. You need hearing protection for that. Now, I'm going to put this right here. I find that it helps a little bit sometimes to increase the area, because what's going to happen, you're going to burn that aluminum foil where that little nut touches it. So sometimes it helps to increase the surface area over which that electric current surges. So I used a coin right there, and I'll just use this here, the edge of the aluminum. You can use batteries for this. I chose to use an ATX power supply. I'm going to put the positive side on top. I will use a coin right there. And I'm going to put the negative side down here on the foil. So what I'm doing is I'm charging these two metal strips, the saddle thresholds, positively, and I'm charging the aluminum foil negatively, and they're separated by these paper thin transparencies. And so it's creating a capacitor. And when the charge gets high enough to jump through that small gap, then you have the discharge through the gap as well as across this channel right here. And as that electric current surges across that channel, forms like a long discharge, or there'll be sparks in there too, but it's also an actual electrical discharge, like a plasma, because the air is ionized. And as that electric current goes across there, a laser beam will be generated by the nitrogen that is in the air between that channel. And I'm putting this here just for protection. The beam won't burn anything except the retina of your eyes, and I want to make sure I've got safety blocks here to block it so that it doesn't go anywhere else. I've also got these little paper targets so that we can see the actual output. Now here is the lens that has to be used. It's a cylindrical lens to focus the beam to a line on that die, and I will cover that in a little more detail in another section of the video. And I'm going to put this right here. Okay, I turned this table around that the laser's sitting on, so it's just facing the other direction. And so what we're going to do now is, we've got everything in place, so let's make sure our spark gap is like we want it. The spark gap is probably about 3 or 4 millimeters. It's wider than these electrodes are. And so we're going to move the electrodes, and they're going to be like roughly a little less than 2 millimeters and a little more than 2 millimeters on this end. This stuff is the kind of thing you can do by eye if you've done it enough and you kind of get a feel for it. The spark gap is just going to be wider than the channel, but not too wide. There's a relationship between this width and that width, and there's also a limit to what you can do and still be practical before sparks start jumping across the surface of the dielectric, or you punch a hole in the dielectric. So there's a limit, and it's something you got to get a feel for. But the first thing we're going to do is put a target here, and we're going to give it a try and fire it and see if we can get a spot on that target. Okay, it worked. Notice that the sparks are occurring mostly along the length of it. Okay, and I think you can see the spot on that piece of paper, or maybe you can't. Yeah, right there. See the spot there on that piece of paper on the left side of the screen. Okay, so what we're going to do, we're going to turn the laser off. All right? We want to see if there's dual output from both ends. That's important here because you want more of the output to be coming from the business end over here where we're going to be pumping the dye than from the other end. And if you taper the channel, you should have most of the output coming from one end instead of the other, the wider end. We're going to put a card down here, piece of paper that's fluorescent enough to indicate the beam's presence, and we're going to try this again. Okay, and it really does work. I know you can't see it, but there's barely any output at all coming from that other end down there. And as you can see over here on the left side, most of the output is coming over here on this left side. And that's what you want for pumping the dye. There's hardly anything at all coming from this end down here. I can see it a little bit, but not much. You probably can't see it at all with the light shining on it from outside. Okay, most of the output is coming from one end instead of both ends. So, let me put it over here like this. This is one of those things where you'll have to adjust it a little bit. If you're not getting an output from this end and you got a lot of sparks on this end, then that means you either need to move this out a little bit, make this end wider, or make this end a little more narrow. And it's one of those things that you just have to play with until you get it right. I don't have an exact formula for the exact separation of electrodes, the exact angle of that taper, and the exact spacing of the spark gap. I don't have any of that. It's just one of those things that I do by feel until I get it right. And usually it doesn't take too long. Once you get some experience at it, you can put it together pretty quickly. So now I'm going to put this little lens here, this cylindrical lens, and this is what is going to make it possible to pump this dye. But I'm going to put the little lens there, and then I'm going to take my dye cell right here. I'm going to put that right up there next to that lens. And I think it's just less than 10 millimeters distance where it focuses exactly on that cell. And I don't know if this is going to work first rattled out of the box or work very well. You usually have to get the focus just right to get the best output. Let's try it and see how it does. And there we go. We got a laser output. There it is. All right, I'm going to take the camera off so you can see this because it's really barely noticeable. Green visible beam. Right there and right there. I took a razor blade and I kind of trimmed away some of the aluminum here because there were some sparks jumping over the edge of the dielectric and grounding out to the bottom there instead of jumping through the spark gap right there. That's the thing that is real important. Any short distance you have anywhere, especially if it's across the surface of the dielectric, is going to be a preferential path for the electric current to take discharging those capacitors over the spark gap. You can get longer sparks between two jagged points or across the surface of a dielectric than you can between two metal spheres. A spark tracking across the surface of the dielectric will not make the laser work. You won't get a laser output. You may get a discharge or some sparks between the electrodes, but you won't get a laser output. It's not just a bunch of fancy sparks between two rails and then you get a laser. It's not that simple. Things have to be done right. Unless the discharge is very, very fast, this won't work at all. So I messed up my electrodes. I'm going to do some adjusting on them again here and see if I can get the channel just right. I wanted to kind of widen the gap just a little bit to see if maybe I could get a little better output. I'm not sure I'm going to be able to do that though. It looks like it's pretty wide already. Probably as wide as I'm going to get it. Maybe just a hair wider. You don't have a lot to play with there. You get a little bit too wide, the sparks are going to go around those two balls and track along that surface. But it's something you can quickly do and just go by eye. Once you get the hang of it, it's very easy to do. Getting decent results, though, takes some fiddling and adjusting. So what I'm going to do, I'm going to put my little lens right there, back there again, and here we go. Okay, this time it's working a little better. But I've also noticed there's some sparks tracking across the dielectric. And no laser pulse occurs when that happens. That's the problem with widening the gap. Sparks jump around the spark gap. And remarkably, sometimes putting a piece of paper under there will keep that from happening. Why? I don't know. I guess because the paper is like a resistor. Okay, so we need to make some adjustments. Now, here's what we do to make some adjustments to the system. First and foremost, always shut your power supply off. Always unplug your power supply before you start to make any adjustments to the laser. Disconnect the part that's driving the actual high voltage transformer, and also disconnect the high voltage leads from the high voltage transformer to the laser. We want to do that before we make any adjustments to the laser itself. Get something that has an insulating handle and make sure that your capacitors are fully discharged before you try to handle anything. In fact, it might be a good idea to even leave something connected across them to make sure that the capacitors don't hold any residual charge and that you don't get accidentally shocked by the capacitors discharging through your hand or through any other part of your body, especially. So we're going to move the gap back just a hair, make a little bit of an adjustment here, and you want to make it a little bit wider, not much wider. Like I said, you don't have a lot of flexibility here before the dielectric surfaces get ruptured by the high voltage charge, or sparks just start jumping across the surface. Once they start forming a path across the surface, then the sparks are always going to go across the surface. It'll be real hard to prevent them from doing that. Now, with the capacitors completely discharged, I'm going to make some little adjustments to the electrodes themselves. This end right here, I'm going to move in just a wee bit, and I'm going to make this a little wider down here. And I got my spark gap, it looks like 4 millimeters, maybe 5 millimeters. I don't know if that'll work. That may be too wide. It wouldn't surprise me if it is. I might get a few shots before I burn a hole in a dielectric or a spark jumps around something and shorts it out. But we'll just see. I'm hoping I can get a little better output from the die to show you here. Now notice most of the sparks are occurring at the back. I'm not having flashovers. What we're going to do is we're going to put our little discharger back in place to make sure that everything is discharged. Power's off, power supply disconnected. Now you can either do one of two things. If you're getting most of the sparks down here and no output, you can either make this end wider or that end narrower. It's pretty much the same thing. But it's one of those things you got to get a feel for, so I'm going to go ahead and just slowly adjust this. In fact, I'll adjust the other side because I don't want to move the spark gap separation that I'm working with right now. So I'm going to probably, it looks like it's a little wide, so I'm going to move this in a little bit and move this in just a hair. And I think that's about where I'm going to want it right there. I think that'll work. And we'll try it one more time and see what happens. Hopefully this will be the last time. Okay, I think we're in business now. A little more output than I wanted from the other end, but the trade-off here is that the frequency is lower because it has to charge to a higher voltage before it finally fires. But we'll see how this works. Alrighty, I'm going to move that back a little bit, maybe just a hair, and turn it on again, see what happens. And we have a laser beam. Yes, we do. Not much of a laser beam, but it's a laser beam. You certainly won't win any Nobel Prize with this, but it is interesting because you truly made a laser from scratch. That much we can say. Ah, yes, that's it. Very hard to focus on it, like I said, to see anything at all, but a little blast of light there that comes out of there. And if it was not lasing, you would not get anything. You would certainly not get a spot. The light coming out of there would be a diffuse and would be a linear spread of intensity with no definition at all. So this is how we know it's lasing. You're actually getting some definition. There's actually a confined area of intensity as opposed to just diffuse light that would be coming out of there if it was just normal fluorescent. Plus, it changes. If you move it at all, out of focus, it won't do it at all. I mean, you get nothing. You either have it there or it changes drastically. You move it a little bit, you get nothing. See, that's just diffuse light now. Move it back in focus, and now all of a sudden the spot appears again. So that's how you know that it is lasing. It's not just ordinary fluorescence, because you have actually spots that are forming there, and those spots don't occur unless it's focused right. Of course, if you have a powerful enough laser, it wouldn't have to be focused. They don't have that. But this is indeed a laser that is coming from nothing but homemade dye, which is quite amazing. Well, what do you know? I blew a hole through my paper, folks, but you see what the paper was there for. And notice, no lasing. No lasing if you don't have the, if you don't have it just right. But I'm jumping around my paper. But the paper actually did keep, I think, the sparks from tracking along the surface when I tried to increase the distance between the spark gaps. You can see you've got enough energy there to blow a hole through that paper, so you don't want that charge going through your hand or your fingers. Especially not in the other part of your body. But so be it. You see that it actually works, and this is proof of principle that you can actually build a laser from almost nothing with no special gases, no fancy mirrors, no fancy exotic laser dyes, almost literally made out of nothing. One more comment about this piece of paper. It's actually an index card. And you can see how the spark just knocked a big old hole in it. The spark actually is a small explosion. It heats the air expands very quickly, and the force of that explosion is what actually blows the hole in that paper right there. And there's really no burning that appears to take place at all. That's actually an index card I was using to discourage sparks from going around the spark gap. Like I said, I think the reason that works the way it does is because it acts like a resistor, and I think that just discourages the sparks from tracking across the dielectric surface and bypassing the spark gap. The power supply for this laser is one of these little high voltage modules that you can get off of eBay for as little as $3. This is exactly what I use to power this. However, I did a little bit of work on mine because when the nitrogen laser capacitor fires, it can sometimes damage the power supply. So I've got the power supply right here. This is the little high voltage module. Here's the input, and the red is marked for positive, and it takes from 3.6 to 6 volts DC input, and it puts a high voltage DC output. I was only putting less than 3 volts DC into this, coming from a ATX power supply. You can use batteries, but it will drink the batteries pretty fast. I've got another video that shows you how to determine which is positive and negative because they're not marked on this. But I've already got this marked. This is the positive side here. On both sides, I have large 50 ohm, 10 watt resistors. These resistors are really probably what does the trick here. They're the ones that protect the high voltage power supply. And these are little inductors right there. I first put the inductors there on both sides. They're just an arbitrary number of turns, just an arbitrary size wire. I think this is like 20 gauge, 22 gauge, real thin copper wire with insulation. And I just used that solid wire because I could wrap it around something and it would stay in a little coil there like that. But Sam Goldwasser told me there's not enough inductance there to really amount to anything or to matter one way or the other. So he suggested I use resistors, so I grabbed a couple of resistors I had. Part of the reason for having bigger resistors physically is because you need a lot of wattage for the higher voltage, but the main thing is if you had a small body resistor like you see in normal electronics, electric sparks would just jump around them. You just track across the surface. So that's the main reason for having a big ceramic resistor. But you can probably get a couple of these resistors on eBay without too much trouble. I don't think the actual specific values are that important. You've got the module right there, and then of course that's the input, output. And as it is, it works as a wonderful power supply for this laser. That's as simple as it can get. It's only $3 for this little thing right here. You can't beat that. Dye laser super radiant like this is a lot different from a laser that requires mirrors like a helium neon laser or even a ruby laser. The dye laser is more like the nitrogen laser. It has an extremely high gain, even higher gain, such a high gain that the beam from the nitrogen laser can be focused on this tiny box And just along that tiny length of a few millimeters, you will get amplification sufficient for a net gain and a super radiant visible output. The box is made from 4 microscope slides. Now this is very important. I used silicone, and when I say silicone, I'm not talking about bathroom caulk. I'm talking about the type of silicone that when you put it on something, it smells like a vinegar. And the reason you want to use that is because alcohol is going to dissolve most glues or epoxies and stuff like that. Trust me, I've learned from experience. So what you're going to want to do in a situation like this is you're actually going to want to create the box in such a way that 2 of the microscope slides on opposing sides overlap at least one of the other microscope slides, the one on the right here in this video, because what's going to happen is you're going to have clearance along the side there. See, notice right here on the outside of that microscope slide, the one that's facing this direction, you've got the silicone, but on the inside you have total clearance. What's going to happen when I focus the nitrogen laser beam on that glass right there, it's going to form a tiny line on the inside of there, a line of bright laser light, because all the laser light is going to be absorbed right there inside the surface, right past the surface of that glass. And the amplification is going to take place along there. So you have to have clearance right here to where the beam right inside that wall here can pass out either side of it where that line is focused. Because the line is going to be focused along the length here. And if you had taken this wall here and moved it out further, or if you had these layers on the sides, on the insides of the wall, like it is here, then the caulk or the silicone would block the output. So this is real critical when you make a die cell. Now the bottom, I didn't use a microscope slide. I think I just used a piece of plate glass for that because it's easier to cut than microscope slides. But I had to put the silicone around it and fill it and that kind of thing to make sure until I got it to where it wouldn't leak. Just to be on the safe side, it's a good idea to put the thing inside of something just in case it does. Of course, you're going to fill that with a dye. The dye just happens to be concentrated to a great extent to where it will be amplified super radiantly. And it just so happens that the actual power density of the nitrogen laser pulse is so high when everything is very concentrated on a small scale. Now, if this were a flash lamp pump dye laser, you could get a lot more energy in and a lot more energy out. Everything would be taking place on a much larger scale, but you would also have to have mirrors for feedback because the dye would not be as concentrated and it would have to be amplified over a much greater distance. Little cylinder here is not leaked at all, the cuvette, so it's holding really good. I'm very happy about that. If anything, this stuff will become more concentrated as alcohol evaporates. You can get one of these cuvettes to actually hold the dye and not leak. That's why you can't use glues and epoxies and stuff like that because the alcohol will actually dissolve it. The only thing that works is actual silicone. Once you get the dye in there and you want to use another one, a lot of times you end up having to put alcohol in there and let it sit. And then over time it will dissolve and then you can pour that out. Do that several times to get the old dye out and put a new dye in. This is how we're going to make our own laser dye at home. You're going to get a Sharpie pen, the fluorescent yellow. The kind when you shine a black light on it, it's really bright, bright, bright yellow. Get a little cup or something you can put it in. Now we're going to take the lid off, the cap off, and you're going to get a pair of pliers, needle nose pliers, and you're going to pull the chisel out of the top of it right here, the part you write on. And it comes out pretty easy, at least this one does. And so we're going to take that chisel, and you might set that chisel aside just for, sometimes you can take that and put it in water or even alcohol and make a fluorescent juice for other projects, just to shine the laser through or whatever. Once the chisel has been removed and your marker, you're going to put it inside of something because sometimes the dye will run out of the bottom of it. So you want to have it in something that will catch any dye that runs out. So what you're going to do is pour the alcohol in here. You're going to get a small eyedropper here and you're going to very carefully start dripping this in here like this. Okay, there we go. Now I've put my alcohol from my bottle into this little container here and I've slowly taken a little bit of alcohol and an eyedropper, and I've dripped it in here until the alcohol is right there level with the top. And it took probably less than 10 eyedroppers to fill this up. You're putting, after the chisel's been removed, you're putting the alcohol in there, and there's like a sponge type, I don't know what you call it, like a material down there that's like a spongy material that has that fluorescent ink, if you want to call it that, in there. Now, once you get this full, you're going to put the cap back on. And you're going to want to let it sit for overnight. You're going to want to let it sit for a while. The longer, the better. Because what's going to happen is the alcohol is going to dissolve that dye in there. The reason for putting this little cup under it is because in case any of that fluorescent dye leaks out the bottom, it won't make a mess all over the surface that you've got it on. And you're going to leave it, like I said, the longer the better, because you want that dye to be nice and dissolved in that alcohol that's in there. It's going to be a high concentration of dye, and that's what's going to be needed in order to transversely pump it with a nitrogen laser and get it to laze super radiantly in the visible green. You want to get a container or glass or something. If anybody knows about this one way or another, I invite you to leave a comment in the comments section. But I believe that you want to use high-density polyethylene for any kind of container that's going to hold a solvent and maybe even this alcohol if you're going to leave it in there for long-term use. This is not actually high-density polyethylene, but it's only for short-term use. You want to take a coffee filter, an ordinary coffee filter, and you're going to put it in a container like this. And it's real important that you wear gloves when you're doing this, because this stuff here, you don't want to get any laser dye on your hands, period, because laser dyes tend to be toxic. Even the dyes from these pens, I don't know if or how toxic they are, but you don't want to get that stuff on you either. It stains like crazy. Anything you get it on, it's going to be very, very hard to get off. So you want to get this little coffee filter in here. The coffee filter is to strain out any of the gunk that is in there, any of the solid impurities or solid stuff that would render it more opaque to light. So you're going to get your filter and you're going to put it in there like that. And then once you get the filter in there, you're going to carefully take the cap off of one of these. There's our stuff, and it's been sitting here overnight, so it's had enough time to dissolve, and you're going to dump it in there like that. And you should get a bright yellow liquid draining in there like that. And I'm going to take the cap off of the next one. In fact, I'm going to shake it up a little bit this time. And you're going to give this a little while to all drain through there. It really shouldn't take that long. And here we go. That one's nice and concentrated. And I can actually see the liquid coming out of there. So you want to leave it like that for a few minutes until all of it drains out and then runs through the filter and then fills this container. Okay, once you've had it in there, I've had it in there, almost 10 minutes or so. And it doesn't give you a great deal of volume, but you don't need a lot of volume, because the idea here, you're going to be transversely pumping it, and it's going to be right inside the surface where the lasing takes place. I'm going to shake this to get a few extra drops off of it. And then we're going to take this off and then chunk your filter. And what you will have is a very highly concentrated dye, and you definitely don't want to get it on your hands. Some dyes are not that visible. I don't know if you can see in there, but there's a really intense fluorescent yellow liquid in there. The kind, if you put it in a glass, it's going to look like it's glowing. Not literally, but you know what I'm saying. The kind, it would go crazy under a black light. But it gives you a really brightly colored liquid, and that's what we're going to use to as the foundation for the laser that we're building here. Okay, now we're at the next step of the process. This stuff stains like crazy, so put it inside of something to catch stuff that may leak out if it does leak out. Because of the setup I've got here, I've got a weight on the back to actually counterbalance this dye, and I'm hoping it will work. Here goes the actual dye solution that we have put together. Ooh, there we go, pretty stuff. And we just hope it won't leak. As you can see, that stuff is insanely bright. I don't know if you can see it inside there. The color is just very, very intense. And so far it looks like it's holding the dye. Notice how it's all absorbed right there at that surface, inside that surface. And that's what we're wanting in order for a laser to be pumped transversely. The reason the toothpick is glued to this is because I used to have this lens mounted on something and the toothpick was like a little holder and I didn't want to remove it. I taped a cylindrical lens on there. It's a lens that focuses light to a line instead of focusing it to a spot. It's basically flat on the side that's facing the camera right now and it's curved on the other side. This little ruler right here has a lens like that on it, but both sides are curved out. Both sides instead of one side. But it's a lens that's shaped basically like a rectangle rather than being round. And the curved side is long or horizontal, if you will, rather than actually being round like a regular lens. And so what it does, it focuses light to a line. And so, of course, this one's designed to read with. If you look at the room lighting, look at that little line it creates on that dark surface. It focuses the light to a line instead of a round spot. And that's what you're wanting to do to pump a dye with a nitrogen laser. A regular round positive lens, as you see, focuses light to a spot, where actually you get an image of the lights above, an image that's basically a point. And so you have to have a lens that will focus light to a line. You can purchase them off of eBay, I'm sure. You have to look around. There's different places you can get them. This one I think I got off of eBay, if I remember correctly. It was years ago. But it's actually curved on one side, plain old convex, and you want to face the curved side towards the laser. Let me get this thing in focus. Boy, it's not easy to focus. There we go. I've kind of got it in focus. It just won't focus very good because it wants to focus on the floor. One of the pitfalls of using a phone to do all of this. It's curved on the side facing the laser and flat on the opposite side, and it focuses the beam from the laser to a line instead of a round dot.